So yeah, we have like 17 participants and I see that people are joining more. So good morning and good afternoon to all. I would like to start. So myself, Ivan Thomas Varkan, and I'm a PhD student at the University of Naples, Federico II in Italy. And I would like to start this webinar series by welcoming all the participants on behalf of Beyond the Edge. Beyond the Edge is a European Union-funded Marie Curie doctoral network that works on pairwise non-pairwise higher-order interaction in complex networks. We consist of 10 PhD students from various universities and research institutes in Europe, working on various aspects of higher-order interaction, ranging from data to dynamics. The Beyond the Edge Seminar Series is an initiative which is organized by the PhDs to invite prominent speakers working on higher order interaction to talk about their recent research and the latest developments that is happening in the field. And for the ninth Beyond the Edge Seminar Series, we have Professor Sarika Jalan from India. Professor Sarika Jalan is a professor at the Department of Physics at Indian Institute of Technology, Indore. Her research spans a broad range of topics, including complex networks, synchronization, machine learning, higher order interactions, and even financial systems. She currently serves as a session editor of Chaos, Solid Tones, and Fractals, and is an editorial board member of Scientific Reports Nature. Professor Jalan is also an elected executive member of the Complex Systems Society. And previously, she held prominent editorial roles, including the editor-in-chief of Journal of Computation Science and an advisory board member of Chaos. And recently, she has been awarded the NetSci Outstanding Service Award 2025 for her contribution to the network science community. So we are pleased to have Professor Jalan, and I would like to pass the virtual podium to Professor Jalan for her talk.
Thanks, Ivan, I did not know about this such excellent forum of PhD student which you have. So I'm pleased to be here. Let me share my slides, and I think you all can see my slides, correct? And you can hear me, correct? And I would like to tell you that please stop me in between anywhere you get stuck. Please stop. I'll be happy to address any question during the talk and as well as to the end of the talk also. So my name is, as you said, Sarika Jalan, and I am in the Complex System Lab, IIT Indore. And you can also reach me after my talk at this my email ID. And this is my web page talking about what the things which we are doing in our lab. And this is the Google Scholar profile for the entire like insight to the work which we have been doing. So today's work, actually, what I was thinking, like, this higher order interaction, this hypergraphs, at least couple dynamics on networks, that field saw really a boom during the COVID time, like 2020, 2019 and 2020. It was the surge of amount of activities which started there in couple dynamics on hypergraph. And very important contribution which we always see, this is analytical calculations. So we have seen that those who work on this field, that's okay. Those who don't work, in my slides, I will explain. But right now, I'm just trying to bring some kind of motivation that what is the motivation of my today's presentation. So, a lot of things which we do analytical calculation, that is very good. And it's often desirable to have the analytical calculation in order to understand the phenomena, emerging phenomena. But often analytical calculations are done in the mean field limit, or you can say in the thermodynamic limit, by considering that system size are large. And then we perform our simulations with the finite size kind of things. And we show that, okay, there is a resemblance. Our numerical calculation, it match with the analytical predictions. So it means our numerics are correct, our analytics are correct, and then we are very good with that. And today I'm going to show you actually few examples where analytical calculations, like whatever happens in the real world and what is predicted by the analytical calculations, they don't match, and both are correct actually. It's not because of numerical artifact we get some certain result. There is some underlying dynamics through which we are getting certain results. So sometimes in real world, we get results which may be very different than the analytical predictions, and it is correct. So that's why this title which I have written, again, the rise of computation in the age of analytical limits. Okay. And for that, I will take a very simplified model I will take, which is my favorite, this Kuramoto oscillator model. This is not working. Yeah, Kuramoto oscillator. So I'll be taking Kuramoto oscillators, simple phase oscillator with one variable. And I will, of course, go beyond pairwise. And I will tell also why I am going to beyond pairwise interactions. And I'll mostly focus on the finite size effect, because in the real world system, the things are finite in size. And this work has been done like last 5-6 years. I have been working on hypergraphs. And this is my current team, mostly who are focusing on the hypergraphs. Abhishek, Priyanka, Ayushi, and Jayesh has recently joined, who are working on the couple dynamics on hypergraphs. Okay. So with that, without actually wasting any time, let me introduce this model. This is the simplest model and only one model in my entire presentation today. And you can see this model is very simple Kuramoto model, which provides, which has been investigated hugely after Kuramoto showed this model last 30-40 years. This model has been worked hugely to study synchronization because of the interaction. Okay, so I will spend some time in discussing this model. So you can see that your this theta, which is the phase. So this is simple one variable. Of course, your systems are more complicated, but let us assume the simplified version that you have only one variable. So theta is the phase of ith oscillator, and it is changing with time. Okay, and you can see there is some intrinsic frequency. So in absence of any interaction, it will just keep on moving in a circle like this. So because in absence of any interaction, this is a single Kuramoto oscillator, phase oscillator, it will keep on moving in a circle. But now I introduce this pairwise interaction. Pairwise, why I am saying pairwise? This is a sine theta j minus theta I. So you have pairwise interaction here. Each node I is seeing its neighbor and adjusting its phase. Okay. And then I sum over whatever pairwise interaction I am having. Okay. And this is a nonlinear interaction because this is sinusoidal term. So this is important thing that you have to have nonlinear interaction. Right now, I have not taken any network architecture. Okay. That thing can also be taken, but it's all to all. So I am seeing all my neighbors and I'm adjusting my my phase based on the average of whatever I am seeing. K is the coupling strength, how strongly I am interacting with jth oscillator. Of course, that interaction strength can also depend upon whom I am interacting with. Right now, just for the simplicity, I have taken this thing constant throughout or uniform throughout. And here is the simple normalization term because I am interacting with n oscillator. I am just dividing this thing by n for the normalization thing. Okay. This is not important, but you can divide it. Otherwise, frequency, intrinsic frequency in all-to-all network, my interaction with other will give me perhaps more contribution than my intrinsic frequency. So in order to have a trade-off between intrinsic frequency and my interaction, and this division is here is required. So now this oscillator will keep on moving in a circle, and you have suppose several oscillators. Then what will happen? So this is now you have suppose two oscillators. I'll show this thing mathematically, but as soon as you have two oscillators and they are interacting, here you can see they are settled down in the anti-phase synchronization. There's two oscillators. So you can have, because of coupling here, what I want to show or what I want to convey, that because of the interactions, you can have something much more interesting. So now you can see here you have more and more oscillators are joining in the picture. And because of this coupling strength, instead of just keep on rotating with the intrinsic frequency, they can get synchronized despite of being non-identical. It means oscillators have the different frequency. So this is the very simple model, and let's introduce, and it has been applied to the various places. Two things which I am mostly interested currently is the power grid, okay, where this is the small variation of the Kuramoto oscillator with inertia and second order, but this Kuramoto oscillator have been investigated or usually applied in the power grid, in the brain, and many different places, which maybe later on, if someone is interested, I'll come back to again to these slides, okay. So now let's come to the Kuramoto oscillator, a model to study spontaneous synchronization. So you can see why I am saying spontaneous. I'll come to this specific terminology in some time. So this spontaneous synchronization or synchronization is appearing because of this pairwise interactions, because in the beginning they are all, suppose omega is distributed, frequency is distributed in some Gaussian distribution. So without any interaction, and if they start with the different initial condition, they will keep on moving in the isolated fashion. Because of this interaction, they get synchronized. So one very important thing which occurs because of this interaction, that they get complete synchronization. It means theta I is approximately equal to theta j for all time t greater than some transient time. And there are several other phenomena which appears, which I am not focusing, like chimera, etc., and spatiotemporal chaos. I am not focusing on that. So in today's talk, I will just focus on synchronization. And there is a measure of this synchronization, like quantitative measure of this synchronization, which is given by order parameter, which is defined by, this is a complex order parameter, r e to power I psi, that is given by 1 upon n and summation over exponential of I theta j. So you can see, as soon as theta I is equal to theta j, if you take mod of both sides, r will become 1. And in the beginning, when all the oscillator are homogeneously distributed between 0 to 2 pi, mod of this thing will become 0. So R lies between 0 and 1. R is the real quantity. R e to power I psi is the complex. Psi is the average phase. So R0 means complete incoherence and R1 means coherent state. And here this is the very popular why all physicists got interested into such a model, because you can see then in the beginning, so here I have plotted K, this coupling strength versus R. And here R infinity means we are talking about the after the initial transient or in the stationary state, what is the behavior. Okay. So now in the beginning, you can see if K is 0, since because of intrinsic frequency is distributed in such a fashion, R remains 0. And as you are increasing this K, R remains 0. And at a critical point, this is spontaneous, call it bifurcation. And through that, this R is equal to 0 line that becomes unstable. And you have two branches. One is R negative, which is inadmissible. So that's why it's not shown here, because R can take only positive value for the physical example which we are considering. So you have here supercritical pitchfork bifurcation. And through that, R0 stable becomes unstable. And you have such emergence of the second order phase transition to synchronization. And later on, people have shown that you can call it the critical T. So critical T has been shown at Kc for the second order phase transition. And entire mathematics and physics is known. And there's a very beautiful article by Strogatz in Physica D 2000, where he has written a review kind of article from Kuramoto to Crawford. And it's a very nice article. But here the thing is that entire physics mathematics is clear that as soon as, so here you have this symmetry breaking. So here, so between 0 to Kc, the oscillators were moving in the symmetric fashion between 0 to 2 pi. And at Kc, there is symmetry breaking. And because of symmetry breaking, there's emergence of this synchronization. And more and more oscillators. So some oscillators are getting locked here. And as you keep on increasing coupling strength, more and more oscillator, they start following this relation omega I upon Kr. R is keep on increasing, and then more and more oscillators keeps on actually satisfying this condition, and you have very smooth transition to global synchronization. So this is very well understood. Now, what happens if we take higher order interaction? So why higher order interaction? So with this community, I am not going to spend more time, because I believe that most of you, they know that what is the meaning of higher order interaction. So functions of many real world systems is the outcome of collective actions of the group. So instead of pairwise, now instead of pairwise interaction, which is known as simplex of order 1, we will go to the simplex of order 2 and 3. So triangle interaction and such a fashion. And there is huge study in the last 5-6 years where they have shown the need of incorporating higher order interactions, because the as soon as you incorporate higher order interaction, your dynamics may be very different. So that people have shown that many real world systems have higher order interactions. And I have not quoted my own work here. We have also shown recently in the Penance system, we have shown that higher order interactions that exist. So that is last year work. So you have several work for the higher order interactions here. And recently we have physics report also in 2023, combining various entire literature on the higher order interactions. So what we take, we take this coupled Kuramoto oscillator, simple phase oscillator, and on hypergraphs. So let's see what happens. So now here you can see that I have the same model which I had in the second slide, only one equation which I have shown so far. But instead of pairwise, in that slide you have J that was only, I was only interacting with J. But now at the same time, I is interacting with K. And what is the meaning of triangle interactions here? Because this is the nonlinear term here. So you cannot decompose this into the two pairwise interactions. So this is genuine higher order interaction. So you cannot have a decomposition into the linear combination of suppose pairwise interaction or nonlinear combination of the pairwise interaction. That's not possible. So now here you can see summation is going for J, K from 1 to N. And since now we have N square term for all to all interaction, if it is not all to all, I will put BIJK kind of hypergraph here. But right now it's all to all interactions. So you have here, instead of division by N, we have N square. Intrinsic frequency remains same as in the previous one. Suppose, for example, Gaussian or Lorentzian distribution. And as soon as we do this, what do you expect? What kind of synchronization we should have? So it turns out there is no synchronization at all. This K2, it denotes that we have simplex of order 2. So instead of K, it's a K2. So you can see that R is equal to 0 remains unstable state for all value of K2 actually. So there is no synchronization which happens into forward direction. I will start forward direction means when I start with the random distribution of the oscillator from K is equal to 0. I don't see any synchronization here in the forward direction. So it remains 0. So what people have done that, and this was already in PRL in Skardhan and Ranas, and later on we also did several studies with the several adaptation of such kind of model. So now what one does, suppose one takes pairwise also and higher order, because when one has a pairwise, we found second order transition to synchronization well established. When we have higher order, there was no synchronization. So because there is a frustration in the system, and it mathematically also one can show very well that R is equal to 0 remains the stable synchronized state. But now when I take this both things, so what happens here, this higher order interaction that is introducing the frustration, which I am keeping on control. So I'm fixing K2 and I'll increase K1. So what will happen? So now I'll start thinking of getting synchronization, but because some frustration which is caused by this higher order interaction. So K1, it supports the synchronization that we saw for the pairwise interaction, but K2, as we saw in the previous slide, it suppresses the synchronization. So now there is some kind of tussle between K1 wants to synchronize the things and K2 wants to prohibit the thing. And because of such kind of fight between these two things, a very nice phenomena that appears. So for pairwise, we have this kind of synchronization, very smooth transition, and higher order, there was nothing. Now when we have both the things, what we get a jump. We get a first order transition to synchronization, which is given by this yellow lines. So purple here is for when there was no higher order interaction, but because of yellow, you get a jump here. So in the forward direction, it means when you start with the incoherent state, instead of this supercritical pitch for bifurcation, now I have subcritical pitch for bifurcation here, and you get a jump here. In the forward direction, if you follow my cursor, I am increasing the coupling strain. I am still in the synchronized state. And in the backward direction, what is doing a backward direction, that I start with the synchronized state and I decrease the coupling strength slowly, adiabatically. Then what will happen? It doesn't desynchronize here. Oscillators, they don't desynchronize here. There's a hysteresis. So here the thing is that I start from the coherent state and adiabatically, very small step, I am decreasing the coupling strength. And I have this hysteresis, and here you can see there's a saddle node bifurcation. This is the unstable orbit, and I will show all this plots also. There's a stable state and unstable state, they meet and they collapse. So this is saddle node bifurcation, and trajectory jumps to there's only one global stable state, which is r is equal to 0. So this happens when you have the higher order interaction. So you can see here, and this is entirely investigated by several people. And this is known as, so entire this R dot, so equation of R, one can write down in this is known as Ott and Tenson manifold. So instead of n oscillator, so you have n differential equation. And currently you have only one differential equation, where R is the order parameter, K1 is the coupling strength for simplex 1, K2 is the coupling strength of simplex 2. And you can actually analytically draw the entire bifurcation diagram for such kind of n-dimensional one. So here you can see n is not playing any role here. So Ott and Tenson approach is performed in the thermodynamic limit. So you don't have any n here. Okay. So there's no finite size correction. So these are the phenomena which you get. Supercritical pitch for bifurcation when K2 is equal to 0. So when K2 is equal to 0, those who know the linear stability analysis, very quickly, this is a home, they can do it with the pen and paper, and they can see that how R is equal to 0. So you can find all the fixed point of this equation by putting R dot is equal to 0. So for R cube, you will get 3 solutions, and R5, you will get 5 solutions. And then you can do linear stability analysis in order to see at what value of K1 and K2 they will become stable or unstable. In that fashion, you can actually reproduce this entire stability or bifurcation diagram. Okay. So this is the entire background which I was actually building up. And now let's see that what happens. So this, we also did a lot of work here in last 4 or 5 years. And only in the last year, we thought of actually thinking of something with respect to n, because this n is not appearing into here. So let's see now what we want to do. So you can see one point here. I want to just bring your attention on something. So this is the entire phase diagram. So you can see as K2 is increasing, hysteresis is increasing, and this is unstable orbit. So if you can see in the potential landscape, here you can see this is unstable one. So if I am below this unstable branch, I'll be dragged to R is equal to 0 case. And if I'm above this branch, I will drag to the R is equal to 1 case. So you have one unstable solution of this order parameter, and both side you have stable solution. One is incoherent and one is the coherent solution. So in the potential landscape, this will be like that. So my finite size effect has entire things which is embedded here in this particular understanding here. So if any question, please raise your hand, unmute yourself, and please feel free to ask. Because now I have filled up the background and I am going to present the results, which is our recent result of last 2 years. We have been working on finite size. So analytical calculations are done by considering the thermodynamic limit. Okay. But you know that real world networks are finite in size. Okay. So since real world networks are finite in size, like for example, you can see that this is serial guns neural network size is 297. Jakhare Karate Club anyway, very small size. Brain network also having some finite number, worldwide air transportation number, some finite size of n which is there, whereas Ott and Tenson approach and all those diagram, that is for the infinite by considering that network size is infinite. Okay. So the thing is that here you have the j is equal to 1 to n, some finite size of the networks, whereas Ott and Tenson approach, when you do the continuity equation, and after that Fourier series expansion and everywhere. So you consider that your network size is infinite, and I perform those numerical calculation are done for n is equal to suppose 10,000, 20,000, and then you show that it is matching very well, and then you are happy with that. But what happened when we have the finite size of the network? So it's small n. Let's see, and we'll also talk about how small we will call the small n, that also we'll see. So here you can see is the result when you have the, so let me focus, let me explain this result also quite. So it's the same diagram. I have plotted R versus K. Okay. So average value of R after initial transient, I discard the initial transient and then average over sufficiently large time in order to avoid any fluctuations. So here I'm starting from 0, for example, and I am going into the positive direction. By the way, you can see that higher order interaction also lead to the synchronization in the negative coupling strength. That is also one very well-established fact for the higher order interactions. But anyway, so now you can see, so let's focus on first of all this triangle. Triangle is for 300. Network size is 300. K1 is equal to 2 is the critical coupling strength that analytically we have already seen that K1 is equal to 2, you get the transition to the second order in absence of higher order interaction, and in the presence of higher order interaction, you get the transition at 2. So what happens that you can see that if you take the network size finite, you get a transition early. So n is equal to 300, you can say you are getting transition below 2. You can keep on decreasing. If you keep on decreasing this network size, transition is happening earlier and earlier. This is for 100. It is happening even below 1. And n is equal to 50. It is happening just as soon as you put the coupling from 0, it has a transition, correct? And the backward direction is not getting affected. So you go to the forward direction, again you start from the synchronized state, backward direction, that is not actually getting affected with this finite size effect, but only forward direction. So any idea, since it is not the in-person class, I cannot see all of you. So I would like to ask this question to you, if you have any idea that why we are getting this, and there is no numerical artifact. It means it is not because of some numerical problem which is there, but it's something genuine which is there inside the system. So maybe some of you might have worked it out by now that, there is no critical coupling. So analytically, we have shown that there's a critical coupling in the system. As soon as you have coupling strength which is strong enough, you should get such kind of bifurcation, supercritical or subcritical bifurcations. But in real world system, when we perform the experiment in the real world system, we find there is no critical coupling, for example, here. And this is something quite, because then system can jump to the first order state, or system can experience this kind of thing anywhere, and that is not we want. So we want to understand that why this is happening. So analytical predictions fails. That is also one thing, because it can jump here, it can jump here, it can jump anywhere. So analytical prediction somehow is failing. And the entire, actually, the key that lies with this unstable state. Because you can see this is stable state and there is a one unstable state. And I would say that that's why analytical calculations are important, because without analytical calculation, you can never determine this unstable state. So numerical calculations for the larger size, they will give you only the stable state. Numerical calculation will not give you this unstable state, but because of the analytical, this Orton-Tenson manifold, which we have written, you got several solutions, and with the linear stability analysis, you find that one of the solution is unstable. So entire this thing lies here in the presence of unstable state. And how it is so that I am going to show you in the second slide, in the next slide. So analytical prediction fails, and this thing lies into the fluctuations. So R has a fluctuation which is the order of 1 upon root n. So if you see this definition of R, which I have written down in third, fourth slide, you have 1 upon n root over a to power I theta j. So, because the finite size, though theta, I am taking homogeneously distributed between 0 to 2 pi, correct? But because of there's a finite size in the system, you can have some fluctuation in the value of R in the incoherent state. In the coherent state, you don't have any fluctuation. And if you see this 2000 paper by Kuramoto to Crawford, Stogatz has discussed actually all this aspect there. So you have this, you can actually very well see, you can do the mathematical calculation and you can calculate the fluctuation in R, and mathematically one can show that you have the fluctuation in R. in the incoherent state when oscillators are distributed between 0 to 2 pi. So now here you can see here what is plotted in the left diagram where my cursor is. I have plotted T versus R. So suppose my K1, that is 0.8. 0.8 is like here. Okay. My analytical prediction says that transition should happen here. But suppose I am taking K1, which is 0.8. And based on my analytical prediction, I am sure that I am in very safe region. I am having the incoherent state. My trajectory is very safe. There is no subcritical bifurcation, because subcritical bifurcation is very dangerous, like you have a stable state that becomes unstable and trajectory jumps anywhere in the space. So you are very sure that we are at 0.8. So I am plotting this R versus T for 0.8. And you can see because of this 1 upon root n, if my n is finite here, for example, some value of n, which I am not remembering because I don't have y-axis, but because of that you have suppose some fluctuation, and this is the order. So it's not like this is equal to 1 upon root n. This is the order of 1 upon n, 1 upon root n. So because of, you can see that if you have, suppose n is equal to 100, 1 upon root n is 10, this is 0.1. So fluctuation is the order of 0.1. And if you keep on decreasing the n, then fluctuation, this R, fluctuation in R, that will keep on increasing. And you can see that maybe at certain point, if this fluctuation crosses this unstable boundary. So as soon as I'm crossing here, I will jump to the another stable state, because this is the basin of attraction. So basin of attraction for this stable state is defined by this unstable boundary. So as soon as I am above this state, my basin of attraction brings me to the synchronized state. So even though despite of analytical prediction says that because of this fluctuation, it may happen, and it may happen at any time. So you don't have exact time. What you can do, you can talk about the average behavior or something, average time you can talk about it. You can bring this concept of StatMech, like first exit time, that first time when the trajectory leaves the R is equal to 0 state. And it can happen anytime. Different realization will give you different, because there's a fluctuation in R. So if you have different realization or different coupling strain, different intrinsic this thing, you can have at different time such kind of jump. Okay. So now K1 is equal to 0. You have this kind of thing. K1 is equal to 0.8. You have the jump here. And this is the, because you can have jump anywhere. There's no deterministic thing. This is the entire stochastic stuff. So what we have done, we have plotted R versus PR for various value of network size. And as you can see here that as network size is increasing, this fluctuation is smaller. Okay. So you will require larger coupling strain in order to cross this unstable orbit. Because here you can see this unstable orbit is lying like for suppose for 0.5, the unstable RU is 0.6. So you require very high value of fluctuation, it means smaller value of n in order to reach this state. But as you keep on increasing n, you will see that mostly you are safe here. But as you keep on increasing this k value, you can see this unstable point that is going towards 0. So you can never reach actually at 2. So as soon as you go very near to 2, you will immediately get the jump. So that's why you cannot actually go in the complete vicinity of 2, and hence for the first order synchronization, and hence you cannot talk about whether criticality exists here or not. So that is one another aspect which we have recently very much got interested in, the criticality at phase transition in coupled Kuramoto oscillator, which was very well established for second order. But here you cannot reach here, because as soon as you start coming here, when a very small fluctuation will bring the jump to the synchronized state. So now here one can see actually that R is having smaller, so n is equal to 50. It means if n is smaller, the average time R is taking the smaller value, and you will have the jump in the finite time. So you have to restrict the time, and at least at certain time, whatever small value you take, you will have certain probability to get this jump, because fluctuation can be higher if you take very long time. You will always almost get the jump. But in the finite time, actually, So one requires this finite time, finite size correction, which we have not done, but I'm just saying that such things should also be explored. So this is simple comparison, which is telling actually take-home message here is that for as you keep on increasing the network size, you have for the given finite time, because in the realistic world you have finite time. Given finite time, you will have certain probability to get the jump, and as you keep on increasing the value of n for the given K value, coupling strength value, that probability will keep on increasing. So here we can talk about in terms of probability. So for n is equal to 100, there is some small probability because this n is 100. Fluctuation is larger, but we are talking about K1, which is very small, but still you have some finite probability that jump will happen. And how we have taken PR calculated, like as soon as jump happens, of course, it will stay there. So in that manner, one can actually plot such kind of graph. So, and several other calculations which we have done. I am skipping here because, so when we have pairwise coupling, since you don't have any unstable orbit, you don't see any finite size jump, okay? Because in order to have, here also you have fluctuations because of 1 upon root n. So R will experience such kind of fluctuation, whether you have pairwise or higher order interactions. But in the pairwise, since you don't have any unstable orbit, you have only one global stable state. Trajectory cannot go anywhere. Here also you have only one global stable state. So you cannot have. So you require some bistable region in order to experience such finite size jump. And this triangle interaction gave us the actually room to see this. So, but in any fashion, if you can get this bistability, you will see that jump will happen. So no finite size effect, but here you will have finite size effect. So now if any question until now, then please raise your hand, unmute yourself and ask me the question. So anytime you, yes,
Ma'am, I
please.
have a question.
Yeah,
So,
sure.
ma'am, you showed that R will change as square root of n. And so, like, have you tried to look at like the second moment of R, for example, like?
Are you changing? Sorry, can you please repeat your question?
So
Are
you
you,
said that yes,
yes,
R changes as square root of n.
yes, yeah,
So the fluctuation, there is a fluctuation in R. So
yes.
like, I'm
That is
asking.
order of 1 upon root n. Okay, yes.
Okay. So
Uh-huh.
like, have you tried to look at the second moment of the R, for example?
So you know, as you keep on including higher and higher order term there in R, you will have more correction to the fluctuation, but dominating term would be 1 upon root n here. This is the dominating or leading term. Later on, you will have small corrections they be there. And since we have not done so far in analytical work, such kind of small corrections there, we don't know what effect those corrections will have on our result. So far we have shown this result, which is the numerical one, like this results. This is the numerically we have calculated. So even though if there is some corrections there is lower term, we are not in any position of actually directly relating with our numerical observations. So you may have some corrections there, and that is our plan actually, to actually have some finite size correction introducing in R equation, not intention manifold, you have some expression in R. So there, if one can think that as some stochastic equation and can try to do that. So the point here is that this actually you may have some corrections, but this results remains the same. If I address your question correctly.
Yes. Okay. Thank you.
Any other question? So you may keep on thinking the question. So, and then as I said, the criticality thing. So second order phase transition criticality has been well defined. But this jump in the forward direction, since because of the finite size effect, you cannot actually reach very close to the vicinity of the critical point. But you can do in the backward one, because backward does not suffer with these fluctuations. Backward direction R does not have this fluctuation. So it means you can go very close to nearby to this this critical point, which is critical T in the sense in the saddle node bifurcation you are having. And I should not say critical T because it has not been proven so far whether you can call it really the critical point or not. It means whether the relaxation time it diverges or not. Okay. So this is our recent work again, driven by all these things, the forward critical coupling in the second order. First order, since we cannot go in the vicinity, we cannot talk about whether there's a critical T which exists or not, but in the backward direction, we have actually shown. So this is my last result actually, as to say, and after that I would like to have more discussion, few things in much more better manner. So now this is the critical, this point you have the transition. So now here you can see is a rescale thing. So x-axis you can see is, I'm talking in the vicinity, it's a -4 into 10 to the minus 3. So you can see x-axis I have zoomed, and the y-axis also it's a zoomed near critical T. So here one can see that if you take the finite n, you get some effect. It means it is not exactly matching at the critical point. It is going like this and then jumping to the 0. It is avoiding this critical point, but we cannot call it finite size effect because as we keep on increasing n, you have more avoidance. You are not going closer to the critical point, which was there in the forward direction. As you keep on increasing n, it was going towards the critical point, and hence it was finite size effect. But here, as you are increasing this n, it is going a bit away, and away means now you can see we are talking in such a zoomed scale. So now this is interesting thing to calculate the relaxation time. It means higher and more deviation. So relaxation time means here, let me define. You start from anywhere to the suppose synchronized state. Okay. So below 0, it only one global attractor which is there, that is R is equal to 0. For K is equal to 0. For K2 is equal to 8, you have R is equal to 0 is the only global stable state for below for K1 is equal to 0. So you start suppose from here, you start from here. How much time it takes to actually drop to the 0? So if there is no critical T, if you go very away from this critical point, right now you can see it's a scaled version, it's a zoom version. We are talking about 0.0001 vicinity. So if I'm here, immediately it will drop down to 0. But near the critical point, this is we have plotted. So -5 means -5 into 10 power minus 3 means we are still away from the critical point. So the time it takes, so R versus T, time it takes starting from R is equal to suppose 7.3, how much time it is taking to drop down to R is equal to 0. So as you are going closer to the critical point, you can see the time which it is taking to come to 0, that is increasing, and actually it is following a power law. So this is our recent one. So divergence of relaxation time near the desynchronization point, and that we have shown that this is a universality, and universality in the sense that saddle node bifurcation also happens. So people have shown already in the mathematics literature that for any dynamical system having saddle node bifurcation, such kind of universality that exists near the bifurcation point. So we have merged these two things. We have found the same universality for the coupled Kuramoto oscillator for the hypergraph. So in presence of higher order interaction, coupled Kuramoto graph also show the same universality, which is shown by the saddle node bifurcation in mathematics. So we have shown this phase transition and bifurcation, which we have merged together. So with this, let me conclude because I would like to have more questions so that I can explain in certain direction in the more better fashion. So finite size effect. So you have fluctuations in finite ensemble can induce phase transition, and when no critical point exists in the thermodynamic limit. And transition mechanism, because higher order interaction create multi-stability, and because of that, this finite size effect that happens. These are certain recent reference, though you can have a Google Scholar profile from 2000. We have published systematically, we have published a lot of work on higher order interactions and a lot of analytical work. And only in 2002 years back, actually, we started thinking about that, what happens in the finite size thing. And we found that this deviation and then in the finite size that has interesting phenomena. And then we have extended that effect in finite size in the Kuramoto oscillator with inertia. So with power grid, you require inertia term. So that is also very area where hypergraphs work has been less done. So without inertia, you have a lot of work in the coupled Kuramoto oscillator. But as soon as you put inertia term there, so we were actually the first people in 2024, our first paper came where we have done coupled Kuramoto oscillator with inertia and the triangle interaction. And analytically, we have shown the entire results there, and that is analytical results. And then after that in 2025 in the same spread. So today's talk, I'm just focusing on the finite size. So I have only put the reference, which is about the finite size. So with inertia, you get a much more richer kind of stuff, which we have tried to do with the, we have tried to see the role of the finite size when coupled Kuramoto oscillator with inertia. And this is the latest one, which is still there in archive, where we are trying to show the what is effect of this critical. So you have this desynchronization point. So you have saddle node bifurcation. What we can talk about the criticality there, because that does not actually have any this thing because of the finite size effect. So with that, this is the review article for the reference anyway. So this latest work is not there in this review. Review article come in 2023. And I am advertising this because I am also one of the author there, and I have tried to review almost all the work in the coupled Kuramoto oscillators on hypergraph until 2023. And so here we have not talked about the finite size. So this is after that. And future direction, immense future direction, because so far I have shown all the results for globally coupled network. When you put adjacency matrix, you can have many counterintuitive result. First thing is that as soon as you put adjacency matrix, you don't know at what coupling strength you will get the first order jump, even though with the triangle interaction, what trade-off should work in order to get the jump. So that is the first very important open area of research, like including real world system. And then finite size effect plus inertia. This is still at the nascent stage. We are trying to understand. This is something recent which we have been doing. And since this was the forum, I thought, let me advertise my recent work on the machine learning. And our step is again to understand this first order jump. So this work also trying to understand this first order jump in the more machine language manner. So with that, this is my lab. Machine learning work is done by Dishan. These are other people. Sanket was the person when I started this higher order interaction. So he did something with the Stewart-Landau oscillator and higher order interaction, but he finished his PhD and has gone Czech Republic recently for his postdoctorate. And you have multi-layer, etc. Again, whenever you can get this bistable state, you can think about this finite size effect. So with that, thank you. And I would like to acknowledge my grants like Sir Power Grant and Vajra Grant. And I'd be very happy to take any question.
Thank you, Professor Sarika, Jalan. So now we could take a lot of questions. We have time for that.
You can also write down your question in the chat box if someone has the problem with the mic. I can read also in the chat box. And
Ma'am, I have another doubt. It's not regarding to your talk. It's about D-dimensional Kuramoto.
Yeah. Yes.
So, ma'am,
yeah, please.
So, do you also observe like finite size effects in D dimension as well?
So, as soon as you have this bistability region, you should have some unstable branch and two different basin of attraction. So anywhere you will have this. And then if finite size is driving the fluctuation in the order parameter of your system, you will get the finite size effect because you will have different basins. So what noise is doing, so the thing which I had shown very briefly there in one of the slide, which was this one in the beginning itself. Let me again come back to, yeah, this one. So this is something like, you can see this is like a valley, you know. So we have two stable one is here and one is here. And because of R, you have fluctuation. It drives my ball to reach here, then it will come here. And then again, the fluctuation will drive, then it can come here. But I said that in a global state, synchronous state, there's no fluctuation. So you have, whenever, suppose you are here in the incoherent state, and there's a fluctuation because of the 1 upon root n, you can immediately jump to the fluctuation is large enough, then it can jump to the another global state. So this is true. So, you know, any system which you have unstable orbit, unstable state, dividing two stable state, making two different basin of attraction, you should expect a very systematic finite size effect there.
And like also like can you is there any paper where they have an analytical dependence on n?
No, that's not there. We were trying to do that. So yeah, no analytical depend. So R can have analytical dependent on n. This is there. This is very simple mathematics. If you want, after that I can do in pen and paper and can send you. So this dependence one can do very well. Okay. That is irrespective of any oscillator or any coupling. It is directly coming from its formula. This formula, if you take like how R is defined like this, 1 upon n summation over e to power theta j. So when theta is distributing between 0 to 2 pi, you can always take the variance of this and you will find that you will get 1 upon root n. So this is simple mathematics which I can send to you. It has nothing to do with the Kuramoto oscillator. The problem which I was thinking that if one can have such kind of thing in this equation, like if you have autotension, you don't have any independence here. So this R is equal to 1 upon root n is a simple exercise. I can share you after this. Like I have to do in the pen and paper and I can send to you, but it has nothing to do with the which dynamics you are talking about. It has exactly coming from its definition. That because if you have infinite oscillator, they will cancel out. Suppose you talk in terms of circle, e to power I theta j. So for each e to power I theta j, there will be one e to power minus I theta j. So the things will cancel out, but in the finite size, they will not cancel out. So this derivation I can send to you. This is a simple textbook kind of calculations.
I also meant for the Ott and Einstein expression.
No, they have not done. Yeah. Actually, thinking that how to do. So there are several things we thought about, but then we found this criticality more interesting. So we deviated our actually focus on this criticality thing, which is now our main interest that arise. Okay. So we're thinking about, we did some analytical calculation a bit off, but then we didn't complete that. Yeah.
Okay.
Any other questions from any of the participants?
I have a question. Can you hear me?
Yeah,
Yes.
you're audible.
Okay,
Cosimo.
great. So thank you very much for the talk. I was wondering, the results you have shown are related to all-to-all connective networks, right? Or simplicial complexes. And you've shown that the finite size effect come out only if you have higher order interactions, right? So I was wondering.
No, I didn't say that. I said finite size effect will come as soon as you have bistability. So you know this bistability, even you can have in the pairwise if you have frequency mismatch, then also you have bistability. This 2011 when explosive synchronization came, Gardner's paper, then you have bistability just because of frequency mismatch of the connected nodes. So my statement is that as soon as you have bistability, you can have this finite size effect. And higher order provides a very simple mechanism to generate this bistability in all-to-all setup, where you have entire analytical calculation. So that's what my statement was. Yes,
okay.
Please.
Okay, so my question then is a bit modified, but still. Is there like a threshold of how many other interaction you should have in order to get this finite size effect? Because if you had just one triangle and Everything else is just pairwise. Of course, I don't expect to see anything of this financial effect. So I don't know whether there is a critical higher orderness of the system, let's say, in order to see finite size effect.
So I understood your question and I reframe. So reframe the question in the manner. So as soon as you have hysteresis, so your question can be like that. Is there any critical coupling you will get this jump? So, so K is equal to 2, you will get jump, that is in the thermodynamic limit. That is hot intention approach. I can see that if n is equal to infinity and tending to infinity, I'll get a jump at 2. Okay. And what we did, we found even with the 1000, without inertia, even 1000 also, you come very close vicinity to the 2. So your question, which you are saying, suppose you have only 3 nodes. 3 nodes means 1 upon root n is very high. So in fact, this result, if you see this 50, I have some results even for the 50 nodes. You can see with the 50 nodes also, as soon as you just switch on the coupling, it's very near 0. So you have this purple kind of line here. You can see this is for n is equal to 50. You get immediate jump. So for if you keep on decreasing the network size, as soon as you switch on the coupling, you will get a jump. You'll get immediately R is equal to 1. Actually, you will not witness a jump. In order to witness the jump, you have to be there on R is equal to 0 line for certain time. And then if you get a jump, then you can say first order. If n is equal to 3, immediately you will get actually R is equal to 1. As soon as you put K even very small coupling strength, you will find that there is a jump. But I have another thing here. It also depends upon what K2 you're talking about. Like if you can see this graph, let me come to this graph. So here you can see that as you are increasing K2, your hysteresis is increasing, correct? So now you can see that here you require in fact, even lesser fluctuation. So, this entire thing is there in this graph. So your question, when you say that how small should be n in order to see the jump, the thing is that if you want to see R is equal to 0 line a bit, then you should have bit sufficient large value of n. And I cannot give a concrete value of n, because you can see here I have plotted the histogram or probability distribution. I don't have the exact value because you have probability distribution here. So I cannot tell the exact point here at all, like exact value, exact KC. No, I cannot tell.
No, my question
Because
was not about
noisy
sorry.
thing. Sorry. Yeah.
No, my question was not about how many nodes you need to, or how few nodes you need to do that, but fix the number of nodes, how many higher order interaction you need. So suppose that you don't have all the possible triangles in the network. You just start, you have the pairwise network and you start adding one by one the triangles. How many of them you need to see?
That is very good question, actually. That's what I said when I told the future direction in the real world. That is my first statement which I gave, that this jump, how much higher order you require in the pairwise. Exactly the same statement I gave, that in real world network, suppose you start with Idrosani random network, you get second order transition. You take the average degree, which is high enough, you get the second order transition. Now the question that how much triangle you should put in the network in order to see the jump. That's exactly the statement I was trying to make when I told the future directions, that you don't see jumps so quickly. You have to have very large number of higher order interaction in order to see the jump. And how much? No, we don't know. I don't know about this. This is the entire open direction. In fact, Skardal's first paper in 2020, if you see, he has showed 2 examples. One was for the brain network and one was the power grid. So power grid, we tried to see the data. There he showed that taking the real network, you can see the jump. But when I took the data, they also have to put this Kardal Erna's paper, this 2020, this nature communication. So they had to put, they said that they have to put some more triangles. And I don't have access to that data, but they also mentioned, and later on we also tried to see that when we get jump, no, there's no, it's very difficult, in fact, to get the jump if you don't have all to all. So you can see here, let me come to the question. This is very interesting one. Here, you can see this pairwise interaction is the order of n square, correct? So n square pairwise interaction, which is there in the network for all to all. Whereas higher order interaction is the order of n cube, correct? In all to all. So you see here the higher order interaction is such a large scale in order to see this jump. So I can tell you maybe the thing, suppose if we are having average degree 10 for the pairwise, for higher order, you have to take the average degree, which is the square of this. So maybe you should try 100 average degree in order to see this jump. And again, the question is how it should be distributed, homogeneously distributed or where, but I think you have to take very large number of triangle interaction in order to see the jump. That is my, so far, whatever we have tried to learn from the experience, this is the answer, no analytical answer I have. Yeah.
Okay, thank you very much.
Any more questions from the participants? I think we have like enough amount of time for taking more questions. If not, I have like one or two questions. So I might have missed out this particular point. So when you showed the equation for the odd tangents and equation for the R.
Yes.
I might be, but what exactly is the delta R? I might have missed out this point. You might have mentioned it.
I didn't mention actually this delta coming from this Lorentzian. So, you know, Ottentinson, this is 2008, Ottentinson gave this Ottentinson approach. And after that, I think all paper on Kuramoto oscillators actually talked about Ottentinson, and hence I did not show the derivation. So this reduction Ottentinson manifold is possible only when intrinsic frequency distribution is a Lorentzian kind of distribution, or some kind of, there is some other distribution where it can work. But the one which was shown, that was the Lorentzian distribution, because so this delta is the property of the intrinsic frequency. So in general, is for the intrinsic frequency property, which is in general taken 1, because when you do Ottentinson approach, you have one complex integration which comes into picture. And in order to solve that, you require to apply this Cauchy-Riemann condition. And that is only possible when you have such kind of Lorentzian
distribution for the frequency.
Gaussian, it does not work. So this is the property which is coming from the intrinsic frequency, which I did not mention. So thank you. Yeah,
I just want to. Okay, so, and the other thing was, if I'm not wrong, there was a statement made like in the backward direction of R, you don't find any fluctuations for R.
Because when you start from all synchronized things, so backward direction means you start from all synchronized one. So then you don't have fluctuation when you have this definition of R. So definition of R says R e to power I psi, that is equal to 1 upon n summation over e to power I theta j. So if all thetas are equal, you can take e to power I theta j outside that summation. And you have, when you take mod, then left hand side is R, because e to power I psi mod is 1. And right hand side also e to power I theta mod, that is equal to 1. So R is equal to 1 remains. So you don't have fluctuation, but whereas if it is distributed in homogeneous fashion, then with the small calculation of the variance, you will find the fluctuation. So this is the mathematical one. And the Strogat's article, Kuramoto to Crawford, he have discussed actually that you won't have fluctuation because the oscillators are logged. You don't have fluctuations because of all oscillators, they are logged. So they are moving together, there's no fluctuation. So if you have your average frequency 0, it's like you are seeing only the stable only one point in the space, So when they are logged and moving, you don't have any fluctuation which is arising in R. This is constant. R remains constant at that particular value. Whereas in incoherent state, you have so many oscillators. So at different value of time, you will have some different variation in R because this is moving. Some oscillators are moving faster, some are slower. So the oscillators are moving. So if you can imagine that, there will be some fluctuation in the R. That is 1 upon root n. But here oscillators are logged. They are moving just like that, together in a bunch. No
And
fluctuation.
this is
Yeah.
true even for like R values that are not exactly equal to 1, but let's say 0.8,
Yeah,
0.9.
it's everywhere. Whenever this is logged,
Okay.
there is fluctuation in R.
Okay.
There's a
Perfect.
constant value. So for different value of K1, if it is logged, there is no fluctuation in R, even not for 1, for any value.
Okay. Thank you.
Yeah.
Yeah, that was my.
Mm.
Yeah. So if any more questions, we can go ahead with that. If not, I would love to again thank Professor Sarika Jalan for joining. It was a pleasure hosting you from the side of Beyond the Edge. Thanks a lot. And I think that marks the end of the 9th Beyond the Edge seminar series.
Okay, thank you. So still, if anyone has any question, can mail me also, and I would be love to engage and share whatever I have learned during my 5-6 years of endeavor with the hypergraphs. So thank you then. Bye. See you.
Bye.
Thank you very much, Sarika. Bye-bye.
Bye bye. Ciao.